Hello, 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 hello. Hopefully the live is living. Hopefully it's working and you can see my face. I have turned this light on, which I do believe that I generally have on. Hello and welcome to another episode live with us on Baji and Physics, where I'm the host, Baji's mother, and also the person who talks about physics, and we cover physics, astrophysics, astronomy, cosmology. Tonight, we're gonna talk actually about astrophysics mainly by a famous author. So maybe I will wait for a few minutes before or a few seconds before I announce exactly who we will cover tonight. But it is, I actually have a bunch of books checked out from the Boston Public Library once again. And it's going to be all new books that we haven't covered before. But some of these topics we actually have maybe kind of seen before. Welcome to the live. If you're here, please do say hi in the chat. And please do say something. Leave a comment if you see this later on as a video upload. And please do like, share, and subscribe. I will take a moment to share the live and make sure all the settings are working as per usual. Welcome, everybody. Welcome North America, South America, Antarctica, Europe, Africa, Asia, the continent I'm from, Australia, New Zealand, some other spots in the on the earth, Madagascar, we always like to mention. And thank you so much, everybody, for being here. So we have been talking lately about certain cosmology, particle physics, quantum mechanics, and such topics. If you are interested in anything that is pertaining to those topics, please do check out older lives. We have some in-depth episodes on just cosmology, which is the study of the universe. We have a lot of episodes on astronomy. We have some dedicated episodes on dark matter and the candidates for dark matter. We have a lot of episodes, including a playlist on just the planets and the solar system. And for that, we have used an astronomy book, which is, of course, let me get that book. It is within reach for me. It's this book, Foundations of Astrophysics, by Barbara Ryden and Bradley M. Peterson. And this is actually, I wanted to mention, this is an Astronomy for Majors book. Hello, everybody. Thank you so much for joining. Hello, Acacio. Hello, our Tinai or our Tini. Hello. So I wanted to just give you briefly that, by the way, if you're joining, please do like, share, and subscribe. Can we get 10 likes? Can we get 20 likes? Can we get 40 likes? That would be amazing. Acacio is top fan number 1 right now. Thank you, Acacio, for joining. Oh my goodness. Acacio is saying, oh, Andrea, I've been absent from the lives, away in DR in family. Oh my gosh, Dominican Republic, that is right. Acacio is from Dominican Republic, but he lives in New York now. Our T is saying hi. Hello, our T. Hello, Acacio. Hello, Mr. Drew. What is this channel about? Thank you. I did happy. Oh, thank you so much. Good day from Australia. Oh my goodness. I just said hi to Australia. Gazor, Gazzore, Gazor. 7339 is saying, good day from Australia. Well, Australia, I am so happy to see you here. Indeed. Oh, look, there is Baji. Let me see if I can show you Baji right now. He is over there. And unfortunately, I did not position the camera well enough here, I am noticing, but that's okay. We will keep going for now because this is attached to a magnetic phone stand and I really don't want to disturb it too much, and I'm sure it disturbs the audio as well. MM Dow Dum. Hello, Dom. How are you? Mr. Drew to you is saying you cute AF. Well, thank you so much. And can you please like the live, share the live, subscribe to this channel, and share it with your wife, with your life, with your cousins, with your relatives, with your distant cousins, with your brother, sister, mother, father, neighbor, especially. That would be most lovely, my darlings. Thank you for such a warm welcome. Well, thank you for bringing all of the warmth to this live indeed by your sheer presence. So, as more and more people join, my energy levels really start to go up and up and up. But in general, I wanted to say that we talk about and we cover topics from physics, astronomy, astrophysics, and cosmology. And I wanted to say that especially for the astrophysics and astronomy topics that we have covered in the past, especially as well, we have been using books that are like for the majors of those topics. So today we're gonna kind of, or tonight rather, in the North Americas, we're going to use some popular science books, but I wanted to mention that sometimes we do actually reference directly the textbooks that would be taught from in universities for the majors of those topics in astronomy, astrophysics. As well as sometimes we talk about papers directly from the literature. Sometimes, I mean, we have talked about definitely my thesis and my papers some as well, without going into too much detail. We have also used this other book called Modern Cosmology by Scott Dodelson, which is quite a nice reference for cosmology, but it tends to be a little bit dense and too much. So I try to explain the cosmology topics in my own words as well as referencing the book. And with as far as astronomy goes, we also have another very thick book. It is called An Introduction to Modern Astrophysics. I'm looking over there because it's over there, and it's quite a heavy and dense and thick book. So I don't want to pick it up right now because tonight we're actually going to be referencing and reading from. We're going to actually do a book reading of an astrophysics book written by an author that I'm sure many of you, if not all of you, have heard of. So I'm excited to bring to you this book and do a little reading from this book, from this very famous scientist and popularizer of the sciences, especially physics and cosmology. And we will talk about that. And it's a popular science book, so it should be really easy to follow and a really fun read. So hopefully many of you will be joining and sticking around for that, because sometimes it's nice to just kind of, simplify things and read from sort of a simpler text, if you will. And that's what we will do. So this is Astrophysics for People in a Hurry. Can you believe that? We have with us tonight Neil D Tyson, the author of many books, including but not limited to this particular book, which is Astrophysics for People in a Hurry. So see how this book is quite thin. It's a nice holdable book. It fits so nicely in my hands indeed. I don't have to work very hard to hold it or flip the pages. Hello, Harper, my darling. How are you doing? Harper from Pakistan has joined. Dowdam is hopefully still here. I just wanted to make sure I said hi to everybody. Australia, New Zealand, America, South America, US, India, Pakistan, Antarctica, Asia, Europe, Germany. Everybody, welcome. Everyone welcome, and we will talk about the greatest story ever told, which is chapter 1 of this book. So I might just jump in really quickly here. This book is from the library, so any book readings that I'm going to be doing, I will make sure to do pretty soon over the course of the next few lives, including this one, because I do have to return the books to the library. I don't own infinite books, but before launching into the topic, let me share the live. Please do stay with us, and thank you for your patience. Mr. Shadow is saying, hey, how's your day and night going? Hopefully all is well. Thank you, Mr. Shadow. It is going. I did my swimming and I'm ready for this live. What about Madagascar? I mentioned Madagascar in the beginning when I first got started with the live. Acacio, how are you, my friend? I haven't seen you in forever. I hopefully said hi to you nicely. I hope I can keep up. You seem very smart. So tonight's topic is going to be astrophysics, but it's going to be from a very simple and easy to digest book by Neil deGrasse Tyson, none other than Neil deGrasse Tyson, who I'm sure many of you know. He's a great scientist as well as a popularizer of science and physics. So he has his, he hosted the show Cosmos. He has all these popular science books. So this should be pretty easy to follow because it's not one of the sort of textbooks and majors books that we sometimes also use, okay? Like sometimes we get into the details and reference books and topics that are for the majors of those topics. Okay? Cool, because I'm very simple. Oh, you're fine. I'm sure it's gonna be great. So by the way, I have started a Q&A. I don't know if you guys can see this or not, but YouTube has asked me to start this Q&A, so why not? Let's start it. And also, please, can you like, share, subscribe, everybody, and let me share the live. I always forget to share the live. And, you know, it would be nice if moderators were here to help with some of that, with sharing the live, for example. But sometimes I have moderators and sometimes I don't. Or sometimes they're new and they might not quite know what to do, which is fine. We will say we are live. Da-na-na-na-na-na-na. Hello, Harper. Harper is here. You're a mod. So Harper, you can keep an eye on the chat. And if you are here and continue to be here, it would be lovely if you welcome people in the chat and kind of let them know what's going on. If you stick around, and please do continue to dominate the chat, everybody. I always appreciate all your comments, all your chat messages, all your everything. More kitty cats are joining us in the kitchen, by the way. So you might see more little babies. But yeah, I try to read everybody's messages and everybody's chat messages. But when I'm reading, I might just have to go back and scroll later on to see all your comments. So keep them coming and don't feel shy and feel free to dominate the chat. Okay, and if you see this later on as a video upload, that's totally fine. You might want to rewind if you're joining the live later on. And please do go to the beginning and start the video, okay? Thank you so very much. Join us and chat. So, I want to get into the book. Apologies if I'm talking too fast, but I do want to get into the book and make some progress with the book reading, because some people actually really appreciate the book readings and they use it to fall asleep, actually. You know, this voice and the astrophysics, astronomy topics and cosmology is a soothing relaxation topic for many, and some people actually use this to play in the background or something when they're sleeping. So I do want to put a lot of astrophysics value in this particular live stream episode, as we try to do in all the episodes. And so let us get on with it. What do you think about aliens and UFOs? Have you seen any? So, by the way, I wanted to real quick mention, now that you're asking the questions, by the way, we also encourage asking any questions you have about physics and all these topics, any science topics, physics and astrophysics, all that, because that also helps me to address the questions and kind of make the content impromptu for you here. Wait, what is happening? I touched a button. 1 second, please. I touched something, touched one of the buttons by mistake on the live, but here we go, here we go, here we go. So I do appreciate when you guys ask the questions in the chat messages. Harper is saying it's snowing. Is it snowing in Pakistan where you are? Oh my gosh. Wow, is it in the mountains that you live? That is very exciting. So I do appreciate when you ask questions, because that actually helps me to answer the question and kind of add more value, and it actually like kind of mixes things up in the lives and really helps me to make the videos, because we also basically take the live stream episodes and I make a lot of shorts and clips out of it. So please do keep the questions coming. That really helps me, and that really helps to you know, make progress with our chatting and our content, and to make it interesting and engaging for everybody. So appreciate all your questions. Now I'll come to your alien question for sure. So, as far as aliens go, I'll give you my tidbit with understanding extraterrestrial life, because that's what aliens are. Aliens is nothing but E.T. I believe there's a movie called E.T. I still haven't seen it because I'm rather bad at watching movies that I should have watched, and especially things from the West. See, I grew up in the East, so I have watched a lot of movies from there, but I have not watched many movies that are Western, that are popular, famous movies. And E.T. is one of them. I do believe that there is such a movie. So please do correct me if I'm wrong, but that movie, I believe, is about aliens, and that is what aliens are: extraterrestrial. So, not on Earth, life that is outside of Earth. Hello, Adam, my darling. How are you doing? Adam Dolson is here. How very nice. So, extraterrestrial life could be on other planets, right? Within our own solar system, like Mars, could have had at some point some extraterrestrial, some alien life. And also the other point I want to mention is extraterrestrial life of any kind is an alien, right? It could be an amoeba, like a singular cell organism could still be an alien. It might not be as interesting of an alien as they show in the movies sometimes, but that is still an alien. And also, it doesn't have to be a contemporary of ours. So you asked me what I think about aliens, and that's why I'm giving you my thoughts. Aliens don't have to be our contemporary. Like, it's not like they have to be on during our timeline of right now on Mars or something. It could have been there on Mars at some point, and maybe that's not the case right now. So, for example, we've talked about Mars because we've talked about planets a lot on some of these lives, and Mars actually has evidence of liquid water. And because it has evidence of liquid water, that means that there could have been some form of life on Mars in the past. So once again, just because we human beings are here on Earth right now for however many years, thousands, millions, whatever, doesn't mean that aliens also have to coexist during that exact timeline. They could be older. And also, of course, aliens could be on completely other different planets that are exoplanets. So not in this solar system, but in other star systems and planets of those other stars. So for that purpose, exoplanets, which are planets within other star systems, orbiting other stars, would be very interesting and would be something that we want to understand and discover more of. So we have also started to research and search for exoplanets, which are planets outside of our own solar system, and that is a big topic as well. So when you ask me about aliens, unfortunately, you will get this long-winded type of response, because I will point you to sort of the real ways in which you could study aliens or research aliens or think about aliens in an experimental and scientific way. As far as just my opinions on aliens, I'm not sure that I have a very strong opinion on aliens. I can just point you towards the research and in what ways can you approach that question, because it's a question and we can approach it in different ways. Okay, so we can approach it in the way of trying to study if there was life form or is life form anywhere else on this in this solar system, and or we can also look for completely other planets and new exoplanets. And we've discovered a bunch of exoplanets, and so far this is a big topic too. So far I don't believe that we have found any that we think that aliens could be on or something, but because in a sense we have discovered a lot of hot Jupiter, like what we call hot Jupiters and hot Neptunes, so planets that are more like our Jupiter and Neptune rather than more like Earth. So it's difficult, we haven't, I don't believe that there are a lot of big sample of Earth-like planets that we've found in exoplanets. And however, it's a very interesting research topic that we can certainly approach, and that would be another way of approaching the topic of aliens. So as you can see, I talk a lot once you ask a question. So keep it coming if this is interesting for you. Cassio is saying we really are stardust, produce outer space, so we are aliens. So yes, exactly, we are aliens. We that is another great way to put it. We are all star stuff. That's exactly right. So in the sense that like we are all made up of stars and the elements that were made in stars, and then those stars died and spewed all their material into interstellar space, and then those formed gaseous nebula and clouds of gas, and those had energy, angular momentum, some heat, and eventually when they condensated to form something like our solar system, here we are. That's how we were made. The planets were made, the sun was made. Most of the angular momentum went to the planets, most of the mass went to our sun, and voila, we're here. So in that sense, we are all aliens indeed. If it depends on your definition. So maybe what I've been kind of talking about is also that, which is how do you look at the topic of aliens, how you want to approach. If you're interested in, is there more life form outside of Earth, then I would say probably, especially if we find conditions that might be hospitable, and conditions that may have allowed liquid water to exist, such as it did on Mars, we could probably take that as a sign that there might have been life, at least at some point. It doesn't have to be right now. It can be in a different timeline. Okay. Hello, Stay Clever. Hello, Harper. Hello, Acacio. Thank you so much for being here. If you're joining, welcome, welcome. We're talking about physics, astrophysics, aliens, apparently, exoplanets, and astronomy and all of that. I'm actually gonna take some sips of my water and start with the book reading for the night, unless there are other questions that I happen to see before I get started. And if you have questions, please do keep them coming, because I am happy to address them whenever I get a chance. And usually between the readings, I do look at the chat and try to answer the questions, especially the good questions like that have to do with these topics. Life as we know it is so fragile that it's also plausible not to find it outside our planet. Sounds awesome. Namaste. Thank you. Thank you, Els Craze Quay. Thank you, everybody. Appreciate you. So, thank you, by the way, everyone who has joined. Let me make sure that things are good. Still good. Hello, Mr. Shadow. How large is space really? Wow, that is... So, I can tell you that some of the most interesting astrophysics happens quite a large distance away. So basically, as for example, one of the first very distant object that we, one of the, I think it might have been the most first object at that largest distance away that we saw was actually a quasar. So a way to kind of, so when somebody asks how large is space, well, I imagine that they want sort of an idea for, because it's really quite infinite potentially. So maybe you're asking how distant are some of the objects that we have discovered. And to answer that, you should look up the first ever quasar that was discovered. And I do believe, and please double check, that I think at that time it was the most distant object that we saw. Okay, so let me get going, actually, as in get this book started, because I want to it does keep expanding. That's a great point. So this is a cosmology topic, the expansion of space itself due to dark energy. That does happen, and we have talked about that in quite a bit of detail, including figuring out evidence of dark energy and the supernovae data, which confirm that the universe is expanding, and so on and so forth. So yes, indeed. If you're interested, we can talk about dark energy as well. But let's keep going and read this book. Once again, this is the book. It is sort of a small book, nice to hold, and it's called Astrophysics for People in a Hurry. So if you're in a hurry, you're in the right place. Good job, everybody. Let's keep on going. So Neil D Tyson speaks in this book. The first chapter is called The Greatest Story Ever Told. The world has persisted many a long year, having once been set going in the appropriate motions. From these, everything else follows. So this is Lucretius in 50 BC that he is quoting, and so starts the chapter. In the beginning, nearly 14 billion years ago, all the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the period that ends this sentence. So we started very small. So if there's a big project that you're interested in doing, just remember that even the universe started very small, and it's okay to start small. Conditions were so hot, the basic forces of nature that collectively describe the universe were unified. So we think it is true that we have talked about this in other episodes as well, that we think that all the forces, all the different types of forces were unified in the beginning. Though still unknown how it came into existence, this sub-pinpoint size cosmos could only expand. So someone just asked, if our cosmos are expanding, if the universe is expanding, and it is expanding, and not only now, it of course expanded from that beginning of the universe, the Big Bang, and therefore here we are, much bigger than that initial size. Rapidly, it's not only expanding, it's expanding rapidly in what today we call the Big Bang. So the Big Bang is the beginning, and from there on we've been expanding. Einstein's general theory of relativity put forth, maybe I'll look this way. Let me know which way is better. Einstein's general theory of relativity put forth in 1916 gives us our modern understanding of gravity, in which the presence of matter and energy curves the fabric of space and time surrounding it. So, also on these lives, we've talked about Einstein's work in relativity. First, he worked on the special theory of relativity, which came out in the year 1905. And this had to do with inertial frames of reference. And so gravitation was not covered there. But we learned some excellent insights, for example, about light. The speed of light in vacuum is a constant, and how that leads to mass energy equivalence, as well as length and time or space-time relativity and things like that. So space and time being relative. So those came out of special theory of relativity, and then to expand it further and also include accelerating frames of reference and explain gravitation, he worked on general theory of relativity. And so for space and for understanding our universe, of course, we need general theory of relativity, because gravitation is quite important in the universe. Okay? So Einstein's general theory of relativity put forth in 1916 gives us our modern understanding of gravity, because of course the first understanding of gravitation came from Newton and Newtonian mechanics, and in frames of reference where maybe it's okay to not use relativity, we can still use Newtonian mechanics. So classical mechanics or Newtonian mechanics is still fine to use if you're not considering very large length scales or very fast speeds. If you're sort of traveling at a speed much slower than the speed of light, where you wouldn't need that correction, then Newtonian mechanics to describe gravitation is fine. But generally speaking, if you want everything to be accurate, then the more updated, more precise, and more accurate theory for gravitation is general theory of relativity. Okay, so in the 1920s. Is the geometric theory of gravitation published by Siri, Einstein. Please stop. So my Siri has started to talk. So let me put my phone a little more away. In the 1920s, quantum mechanics would be discovered. Another big, how should I put it? Another big movement in physics that happened in the 1900s, in the 20th century, is quantum mechanics. So let's see about that. In the 1920s, quantum mechanics would be discovered, providing our modern account of all that is small, molecules, atoms, and subatomic particles. But these two understandings of nature are formally incompatible with each other, which set physicists off on a race to blend the theory of the small with the theory of the large into a single coherent theory of quantum gravity. Although we haven't yet reached the finish line, we know exactly where the high hurdles are. One of them is during the Planck era of the early universe. That's the interval of time from t equal to 0 up to t equal to 10 to the minus 43 seconds. So 10 to the minus 43 seconds, which is 110 million trillion trillionths of a second after the beginning, and therefore, and before the universe grew to 10 to the minus 35 meters, which is 100 billion trillion trillionths of a meter across. So when the universe was still quite small, and hello, Skeletora. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics. So Planck era, small numbers era, when the time t was equal to 10 to the minus 43 seconds, and the length scale of the universe was 10 to the minus 35 meters. Precisely what happened then is something that we might not be all in agreement about, because remember the two big theories, the two big parts of physics, one quantum mechanics on the one side and general theory of relativity on the other side, do not agree. Okay, this exact topic of this disagreement, the incompatibility between quantum mechanics and general theory of relativity, where basically general theory of relativity is a theory for gravitation, but it doesn't really address things like all the different particles and all their properties like what quantum mechanics does, because quantum mechanics is the physics of the very small. So because of its success, we get the entire standard model of particle physics and all the rest of it from quantum mechanics. So that's all very well, but unfortunately, quantum mechanics does not describe gravitation. There's no explanation for gravitation in quantum mechanics. For that, we lean on general theory of relativity, but then these two theories on the two sides, and it's probably a little bit unfair to just call them theories because they've also had a lot of success experimentally. Those have incompatibilities, and these incompatibilities are especially important in certain scales, okay, in certain extreme environments. Now, like in our day-to-day life, we might not be so bothered by the incompatibilities between quantum mechanics and general theory of relativity, but in certain extreme conditions, those are a problem, and people have fought over it. People have tried to come up with a new theory that unifies everything, and of course that's how we get a grand unification theory and a superstring theory, and that's a whole other topic that we also have discussed in great detail for a while on the lives. But let's keep going. So the clash between gravity and quantum mechanics poses no practical problems for the contemporary universe. So right now in these length scales, astrophysicists, I mean, I don't know if everyone would necessarily agree with that sentence, but according to Neil D Tyson, for the contemporary universe, it's fine. For our day-to-day, for sure, it's mostly fine. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. So this is another way of saying that as long as you accept that the physics of the very large, or the physics of gravitation, is given to us by general theory of relativity, leads to a couple of singularities, but let's just forget about those. General theory of relativity has a lot of success. Experimentally, we have gravitational waves. We have direct measurement of gravitational waves, which of course falls out of general theory of relativity. So it's good. Other than a couple of things, couple of singularities, it's really good. On the other hand, quantum mechanics. Quantum mechanics has great success. We cannot ignore it. We cannot write it off because it kept being successful and kept discovering more and more particles and more and more real truths of this life. But there's this small detail where quantum mechanics does not explain gravitation. There is no gravitation related particle or explanation of gravitation in quantum mechanics. And what people would ideally like is a theory that kind of just can explain everything. But if you're okay with the fact that general theory of relativity is good at gravitation and so good at large scales, and quantum mechanics is good at small scales and explaining the physics of the small, and the people who kind of work on these two different parts, if they never meet because these are two different expertises within physics, then everything is fine. Then our day-to-day is quite peaceful and harmonious. But if the large is the small and the small is the large, which is what was the case in the beginning, or not the beginning, but close to the beginning of the universe at 10 to the minus 43 seconds and before, then there is a problem, right? So back then, the universe was very different. The environment was very different, and who knows, maybe the grand unification theory would be very much not maybe, most likely the grand unification theory would be this complete beast that would explain things back then, and now we see things differently, and the grand unification theory is not only very difficult mathematically, but maybe it's kind of hard to imagine because the universe is no longer like that anymore, and we don't get those same conditions that we had back then. So what happens is, for example, real quick, superstring theory is like impossible to prove out in the current universe. We cannot access those conditions that are needed to maybe prove that out, right? So this is a sort of unfortunate truth, but I don't want to limit our thinking and stay optimistic that maybe there is a better way to do this, okay? So anyways, yes, so Einstein did, Einstein gave us general theory of relativity, which is the theory for gravitation. So in that theory, gravitation is not a force. Gravitation is the curvature of space-time. You're right. But quantum mechanics is a different part of physics, which has the fundamental forces and gives us all these particles and properties of particles that are all very important to also explain. And general theory of relativity doesn't really do that. So they're disjointed. They're incompatible. Does that make sense? So in particle physics language, there are 4 fundamental forces, right? Electromagnetic force, weak nuclear force, strong nuclear force, and gravitation. But gravitation does not have a particle physics explanation. There is no particle that we have associated with gravitation. This is the problem. So quantum mechanics doesn't have a theory for gravitation, which is a problem, right? If you have a big part of physics not being able to explain something fundamental, then that's an issue. Now, coming to general theory of relativity, we do have an explanation of gravitation with general theory of relativity, but GR doesn't explain all the rest. That's over here. That's the issue. And so people took, so for example, people wanted to have a quantum gravity, some unified theory that can encompass all of the physics, the small physics as well as the large physics, if that makes sense, okay? So that's the disjoint that we're talking about. We need unification, and especially we need unification in extreme conditions, which is the case close to the beginning of the universe, when the large universe as we know now was very small. So that's what we're talking about. So, but in the beginning, during the Planck era, so the Planck era is those very tiny small numbers era, the tiny small number time and tiny small scale for the length. So in the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the large and the small, as in maybe there was a shotgun wedding between GR and quantum back then. Alas, the vows exchanged during that ceremony continue to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. So before the universe was 10 to the minus 43 seconds old, as in the very early universe, it's very difficult to explain things. Yes, or close to the singularity, yes. And a singularity itself is a bit of an issue, right? Like I was saying how in general relativity, there's a couple of singularities, as we know. The Big Bang is a singularity, and black holes, inside the black hole, there is a singularity. And that's not very nice either, right? It's fine. It's fine because overall, general theory of relativity is very successful, but at the same time, there's a couple of issues, okay? There's a couple of issues, and we've just mentioned them. Arjun Sinha is saying, hello, what's up? Hello. Hello, Arjun, how are you doing? So we nonetheless expect that by the end of the Planck era, gravity wriggled loose from the others. So we think maybe the four things were unified at one point. But we think that as far as this disjointedness, both in the theories as well as the reality of gravity kind of becoming disconnected from the rest of the fundamental forces, that might have happened as early as that time of the Planck era, okay? And once again, Planck era is t equal to 0 to t equal to 10 to the minus 43 seconds, which is really quite short, but we nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other, still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, so the universe has now aged, to 10 to the minus 35 seconds. It continued to expand, diluting all concentrations of energy, and what remained of the unified forces split into the electroweak, so that is the electromagnetism, and weak nuclear forces, and the strong nuclear forces. So first gravitation split away, then the unified forces split into electroweak theory and electroweak forces and strong nuclear forces, and later on the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare the four distinct forces we have come to know and love, which is of course the ones that I just now mentioned. So those four fundamental forces, right? Those four fundamental forces that are four fundamental forces we think were maybe just one at one point, and what kind of led to them splitting up is what we're wondering. Hello Dibbo Jyoti. Hello Dibbo Jyoti Shaha. Is space-time actually infinite at a singularity? Is that just an artifact? That is a great question. You're cute when you smile. Oh, thank you. It is where our math breaks down, so we're unable to describe it. So yeah, so singularity is a mathematical breakdown. Whether singularity means that we don't have a mathematical description of that exact moment when the universe started, okay? So that's a singularity, and so is the inside of a black hole. So yeah, anyways, I would say especially, so another thing you have to keep in mind is some of the history that goes along with all of this, right? Like, it's not just that we're spewing random facts at this time. We have built up to this point, right? We've built up to the point where we have four fundamental forces, but also we have some hope of unification. Unification would be, if unification was so hopeless all the time for all the things, then maybe we wouldn't be talking about it so much. But we actually did kind of unify some of it already, right? We've unified electroweak, for example, like we've unified the weak nuclear force with electromagnetism. So there are certain conditions where electromagnetism and the weak nuclear force are unified. So that also gave some hope and some beauty, symmetry, if you will. Basically, there's some symmetries like that in nature that we're finding that allows us for the unification of things, and then strong is kind of unified. So it really is, it would just be so much more beautiful if gravitation could be unified with the non-gravitational fundamental forces. And also the non-gravitational fundamental forces are described in quantum mechanics and particle physics. So, it's just this, like, it's just that, like, missing piece at this point. It's the missing piece of the puzzle at this point between these two things. Okay, so a trillionth of a second has passed since the beginning. All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as their particles, was incessant. So we're not talking about the early universe. The universe was hot enough for these photons to spontaneously. So by the way, I'm very glad we're reading this by Neil D Tyson, because actually we have also studied this in cosmology, like in a more detailed manner in a cosmology context. And describing the very early universe is not so easy. We have delved into it in some detail, but it's not so trivial, actually. So I'm kind of glad that Neil deGrasse Tyson is doing it in such simple words in this book. So let's keep going. All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as their matter, was incessant. The universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs. So we have talked about particle antiparticle pairs quite a bit. And that's what a photon, like a gamma ray, would do that, can actually make, for example, an electron-positron pair, okay? So yes, antimatter, or sorry, the universe was hot enough for these photons to spontaneously convert. So this this interaction, if you will, or how do I put it? This conversion of photons to antimatter pair, say for example, a gamma ray going into a electron-positron pair, was happening a lot spontaneously, okay? That was how the environment was back then, where that type of conversion can happen spontaneously. So that was happening, which immediately thereafter annihilate, returning their energy back to photons. So the thing is, like, if this was kind of going back and forth, photons going into electron-positron, electron-positron going back to form photons, because once again, if you annihilate electron and positron, then you get a photon from that. So this type of thing was sort of in equilibrium, constantly happening. So yes, antimatter is real. So antiparticles, pretty much particles having an antiparticle partner, that is a thing in nature. It is supported. And we discovered it, not science fiction writers, these transmogrifications. I don't think I knew that word before. These transmogrifications are entirely prescribed by Einstein's most famous equation, E equals mc squared, which is a two-way recipe for how much matter your energy is worth and how much energy your matter is worth. So matter goes into energy, energy goes into matter. We know this. As I was saying, that we actually know this from 1905. 1905 is when Einstein gave us special theory of relativity, and right then we got space-time, the fact that space-time is relative, and also the fact that mass energy is equivalent, as in mass can be turned into energy, energy can be turned into mass or matter. So this whole thing about photons going into becoming electrons and positrons as in an electron-positron pair, antiparticle pair, and then those things annihilating to basically give you back a photon or a gamma ray. And in fact, that's how you write that equation, by the way, in a, say, particle physics-y kind of way. You would say electron-positron going into a gamma ray with the gamma symbol, or gamma ray going into an electron and positron. That's how you would write it, okay? This was happening just nonstop, constantly in that early universe. Yes, so there are more processes that make matter than antimatter. So that's why matter won. Okay? We can talk about those processes, but basically there are more ways in which matter is made. Okay? So because this equilibrium that I'm speaking of right now, the antimatter matter going into photon going into matter, antimatter, this was in the very early universe before. So in that era, in that early era of the universe, later on, you actually have different things happening. We will see, and we end up with more processes that make matter than antimatter. So the c squared in E equals mc squared is the speed of light squared, a huge number, which when multiplied by the mass reminds us how much energy you actually get in this exercise. So you can get a lot of energy from just a little bit of mass. We also know this because of the atomic bomb, unfortunatamente. You know, so there's also that, a violent bit of evidence as well. Shortly before, during, and after the strong and electroweak forces parted company. So Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething soup of quarks, leptons, and their antimatter siblings. So all these particles, quarks have anti-quarks, leptons have anti-leptons. Everyone has their antimatter partners, or in this case, he's calling them siblings, along with bosons, the particles that enable their interactions. None of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. So he's just kind of mentioning all the particles at this point. So as you know, because we have talked about it in our particle physics discussions, there's really only three families of particles. These are leptons, quarks, and bosons. So lepton example would be the electron, quark example would be like the up quark, which is within protons, and neutrons within the atoms that make us up, for example. And then boson example would be the photon. So pretty much all the forces are kind of mediated by bosons. The particles that are interacting are either quarks or leptons. Okay, so again, all in all, just the three types of particles really that encompass the standard model of particles, which is just leptons, quarks, and bosons. Really just the three. Okay? And all of the well understood particle physics kind of falls under that. So none of these particle families are thought to be divisible into anything smaller. So the ones that I just mentioned are pretty much the fundamental families, okay? Do you believe in the Big Bang, and why? Yes. And why? Short answer would be because the universe is expanding. Okay. Expansion of the universe is one of the evidences for Big Bang, okay? So none of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. As I just now said, those three particle families, but I give you one example from each family. There's actually more particles within each family than what I mentioned. The ordinary photon is a member of the boson family, but there are other bosons too. We're just mentioning photon at this time. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino, and the most familiar quarks are, well, there are no familiar quarks. Each of their 6 subspecies has been assigned an abstract name that serves no real philological, philosophical, and pedagogical purpose, except to distinguish it from the others, up and down, strange and charmed, and top and bottom. So those are the quarks in the quark family, and their naming of them, as he mentioned, are kind of not the best, maybe. Bosons, by the way, are named for the Indian scientist Shotendranath Bose. The word lepton derives from the Greek lepos, or not lepos, leptos, sorry, meaning light or small. Quark, however, has a literary and far more imaginative origin. So, the physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks as the internal constituents of neutrons and protons. So the thing to note about quarks is that even though they have weird naming, quarks do make up protons and neutrons, which are, of course, within the nucleus of all atoms. And so in that sense, quarks are also something that we know about, or something that ordinarily we would think are relevant. So anyways, this person at the time thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. One thing quarks do have going for them: all their names are simple, something chemists, biologists, and especially geologists seem incapable of achieving when naming their own stuff. I don't know what Neil deGrasse has against geologists, but I think he's taking it out here. Quarks are quirky beasts. Unlike protons, each with an electric charge of +1 and electrons with a charge of -1, quarks have fractional charges that come in thirds. Basically, we haven't yet discovered the smallest object ever there is yet to discover. I'm not sure about that, whether it's going to be the smallest object. Are you saying, because, you know, the most, I mean, the small, I mean, smallest in what way? Because photons are massless, and neutrinos have very low mass and they're leptons. So we have discovered some pretty small stuff. We just have some other issues, such as a lack of unification between GR and quantum mechanics. Okay, so you know, let me know what you think, or what that question is. How is it possible that one bang created? So that's a great question. So the Big Bang was not necessarily a bang or big. The name the name Big Bang has stuck for the origin of the universe, but the Big Bang is not necessarily an explosion, or I mean, we know for sure it was not big because the universe started very small, right? So definitely not big, and probably not a bang. Okay, so we're simply suggesting that with the Big Bang, basically, even though the name is Big Bang, it actually says the universe was very, very tiny at one point, and we've expanded to where we are now. So all of the evolution that gets us to this point is supported by that, okay? And it's consistent with the Big Bang, okay? So anyways, quarks have charge that comes in thirds, and you'll never catch a quark all by itself. It will always be clutching other quarks nearby. In fact, the force that keeps two or more of them together actually grows stronger the more you separate them. Goodness. So the strong nuclear force, remember, one of the fundamental forces, is at play here. So once again, the force that keeps two or more of them together actually grows stronger the more you separate them, as if they were attached by some sort of subnuclear rubber band. So kind of like a rubber band, like a rubber band gives you that tension when you try to stretch it. It's something like that. Separate the quarks enough, the rubber band snaps, and the stored energy summons E equals mc squared to create a new quark at each end, leaving you back where you started. So the strong nuclear force is kind of exotic. Of course, it's at play at shorter length scales, you know, length scales of subnuclear particles, or quarks, for example, right? Quarks make the protons and neutrons. So those are like very tiny, or very tiny length scales, especially. So the strong nuclear force is not really something that we might bother with day to day at our length scales, or even at the length scale of like for example, you know, if you get shocked by like electrostatic charge or something, that length scale is very different, right? So so all of that is to say the strong nuclear force might not be something that you come across, but it is important. It is at play, of course, within the subnuclear types of physics, and it works kind of different. It's kind of like that rubber band thing that Neil deGrasse is talking about. During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks unattached quarks to rival the separation between attached quarks. So, do you see now why we think that the forces might have been unified at one point? Because all this stuff about the length scales, right? We see that the strong nuclear force, the weak nuclear force, and the electromagnetic force are important at different length scales, right? The electromagnetic force is a much more longer length scale type of force. So the fact that the universe was tiny at one point, we think they were all the same at that scale. That scale and that environment might have unified them, or might have meant that they were all just the one, but then things kind of detached from each other as the universe changed. Okay, so the universe itself has changed because it was an expansion more than bang that started natural processes of which we are a result. Yes! We do see small pockets of order, yes. Generally, entropy is always increasing in the universe. That's the other thing. In the same direction where we're expanding, as in the forward direction, this is not a Back to the Future movie. Another movie that I have only half paid attention to, but but in the direction of forward time, the universe expands and also entropy increases. So we're not all that orderly, actually. Even if there is order, there is more disorder. The infinite intelligent order of things cannot be created from chaos. There needs to be a super intelligent creator. Okay, that's totally fine to believe. We are doing physics, astronomy, astrophysics, cosmology, however, not theology. I have no expertise in theology, so there is that. During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves in spite of being collectively bound to one another. What an interesting environment. The discovery of this state of matter, a kind of quark cauldron, like in Harry Potter, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories, Long Island, New York. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry in which particles of matter barely outnumbered particles of antimatter by about a billion and 1 to a billion. That small difference in population would hardly get noticed by anybody amid the continuous creation, annihilation, and recreation of quarks and anti-quarks, electrons and anti-electrons, better known, of course, as positrons, and neutrinos and anti-neutrinos. The odd man out had oodles of opportunities to find somebody to annihilate with, and so did everybody else. But not for much longer. As the cosmos continued to expand and cool, growing larger than the size of our solar system, the temperature dropped rapidly. Yay! Below 1 trillion degrees Kelvin. A millionth of a second has passed since the beginning. So, lo and behold, a millionth of a second has passed since the beginning, and we're already so much bigger and so much cooler. This tepid universe was no longer hot enough or dense enough to cool or to cook quarks. And so they all grabbed dance partners, creating a permanent new family of heavy particles called hadrons, from the Greek hadros, meaning thick. That quark to hadron transition soon resulted in the emergence of protons and neutrons, as well as other less familiar heavy particles, all composed of various combinations of quark species. In Switzerland, back on Earth, the European Particle Physics Collaboration uses a large accelerator to collide beams of hadrons in an attempt to recreate these very conditions. So, you know, we don't have those conditions anymore that we did in the early universe, and so certain things, certain physics can be hard to probe without mimicking somewhat of that type of condition now, and that is done artificially, for example, in a large hadron collider or a some collider, and the famous one is in, of course, Switzerland has one. So this largest machine in the world is sensibly called the Large Hadron Collider. The slight matter-antimatter asymmetry afflicting the quark-lepton soup now passed to the hadrons, but with extraordinary consequences. So universe is continuing to cool at this point. Still very early universe, but very different, for example, than before 10 to the minus 43 seconds. As the universe continued to cool, the amount of energy available for the spontaneous creation of basic particles dropped. During the hadron era, ambient photons could no longer invoke E equals mc squared to manufacture quark-antiquark pairs. Not only that, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe. So the universe expanding also cools things down. So there is that phenomenon as well to combat the rest. Dropping below the threshold required to create hadron-antihadron pairs. For every billion annihilations leaving a billion photons in their wake, a single hadron survived. Those loners would get to have all the fun, serving as the ultimate source of matter to create galaxies, stars, planets, and petunias. Petunias, us, all of the things. Without the billion and one to a billion imbalance between matter and antimatter, all mass in the universe would have self-annihilated. So thank God that that didn't happen. Leaving a cosmos made of photons and nothing else. The ultimate let there be light scenario. It's funny. Let there be light scenario would have happened if there was not more processes to make particles than there are to make antiparticles. And yes, there are lots of galaxies, hundreds of billions. I don't know exactly how many galaxies there are. There are many, many. Without, so now we're at the point of history where 1 second of time has passed. This is the type of history I really like, by the way, guys. I love the history of the universe and its evolution. The universe has grown to a few light years across. So, little tiny universe of 10 to the minus 35 was the length scale, right? Let me make sure. Yes. We were talking about 10 to the minus 35 meters, and now 1 second later, it has grown to a few light years across. That is how important the expansion of the universe is. That is how important understanding dark energy would be. Do they also have their own big bangs? No. So, galaxies are not the same as universe. Galaxy is simply clumping of matter in the universe. You should definitely listen to my cosmic microwave background radiation lives. We talk about the CMB. and the smooth universe in several episodes. And you will see how the universe, when it was around 300,000 years old, there is some leftover photons that we can measure, and we can understand about the smoothness of the universe. But in all of that, the detail is that there are little spots of overdensities. There are fluctuations away from smoothness in the universe. And so, in other words, galaxies are little fluctuations in a smooth universe where matter won, where gravitation won over expansion. We're talking about how, see how there is expansion happening in 1 second after the Big Bang. We are at a few light years across. If there was only expansion, so sometimes expansion or dark energy is called the anti-gravity term. Why? Because if there was only ever expansion and gravitation, which brings mass closer together, which brings matter closer together, if gravitation was never allowed to win, then we would not have galaxies. So galaxies, the way we get galaxies, the way we get stars, the way we get the solar system is different. It's nothing, that is not the Big Bang. The universe started with the Big Bang. But galaxies is simply gravitation winning, okay? Sometimes. On a large scale, that is, once again. If you think about large scale structure, how did our universe, how did matter distribute itself in the universe and on a large scale in the universe? So like we know, for example, we're going around the sun, like solar system, our own galaxy. That is kind of short scale in terms of the universe. Like, do you see how within 1 second the universe had grown to a few light years across? So that you know, universe is much, much bigger than just our galaxy, right? So in terms of cosmology, our galaxy is very local, very ultra local, right? So what I mean about distribution of matter in the universe is like large scale. So the way we have large scale structure in the universe is related to your question about the galaxies, right? So it's a very important question. Understanding large scale structure and how did matter distribute itself in the universe. I mean, of course it has to do with gravitation, but exactly what are the details is a whole research topic, okay? So we'll keep going. The universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars. So by the way, our galaxy is 100,000 light years across at this point. Just to give you an idea for how big things are. And how, I mean, also to give you an idea how big the universe was at that time. Not very big. So smaller than our galaxy at this time, right? Few light years across is not that big. Again, in terms of the cosmos, but this is only 1 second of time has passed. Hello, Brady. You have to be more specific than that, my darling. You are saying the Big Bang created all galaxies? No! The Big Bang created the universe, and the universe much later evolved to have galaxies. There were no galaxies in the beginning. Maybe that's your question, Mr. Drew. There were no galaxies in the beginning. Guess what? In this story right now, where we are at 1 second of the age of the universe being 1 second. Oh, I see. God created everything. That's why I'm wrong. Okay, got it. Well, if God did create everything, then what we're talking about is well within the realms of what's been created, and we're just understanding the cosmology and physics of that. So it should be acceptable to all. So there were no galaxies in the beginning, okay? Galaxies come much later. the universe, after evolving for years and years, that's when galaxies happened. There were no galaxies. We are right now at the point we're not making any galaxies, okay? So 1 second of time has passed. The universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars. So that light year across distance. At 1 billion degrees, it's still plenty hot and still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. But in the ever expanding, ever cooling universe, their days, seconds really, are numbered. What was true for quarks and true for hadrons had become true for electrons. Eventually, only one electron in 1 billion survives. The rest annihilate with positrons, their antimatter sidekicks, in a sea of photons. Right about now, one electron for every proton has been frozen into existence as the cosmos continues to cool, dropping below 100 million degrees. Protons fuse with other protons as well as with neutrons, forming atomic nuclei and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium, along with trace amounts of deuterium or heavy hydrogen, tritium, even heavier hydrogen, and lithium. So deuterium and tritium are simply the isotopes of hydrogen, and lithium is the third element with atomic number 3. 2 minutes have now passed since the beginning. That's where we are in the book, okay? For another 380,000 years. So approximately, like I was saying earlier, 300,000. For another 380,000 years, not much will happen to our particle soup. Throughout these millennia, so that's why that baby picture of the universe that we talk about, the CMB, the cosmic microwave background radiation, where the photons are hanging out, that we can see from this around this time, the 380,000 years age of the universe. That's so very important because it gives us another way to probe the early universe and all the physics of that early universe, including the Big Bang. So the CMB also gives us evidence of the Big Bang, okay? So throughout these millennia, the temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But this freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface, and all the free electrons combine with nuclei. So as things cool down, we can actually make nuclei. So the marriage leaves behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment. Isn't that great? And completing the formation of particles and atoms in the primordial universe. So this is where we have, this is where the CMB is from. Hello, Brady. Smart and beautiful. Okay. She's using evolved. Evolved? I mean, evolution, not the biology evolution. 100 light years is not that big. 100,000 light years. Yeah, 100,000 light years is not that big. Because big is relative. Our galaxy is just a tiny part of the universe right now. So If it's 100,000 light years across, that's local. Okay? All right. We will keep on going for a little bit longer. I'm gonna need to wrap it up actually, because we will continue this. We will continue maybe tomorrow as well. Any other questions, keep them coming. And I loved this last sentence actually. Let me read it again. This freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface. And all the free electrons combine with nuclei. The marriage leaves behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment. So, by the way, this is a great sentence. This is a very nice way to put what we said about the cosmic microwave background radiation in my previous lives. I don't know if that was my last live, or certainly a few lives have been spent on that. And so definitely go check that out, because we talk about little overdensities in that CMB map. And a great way to understand or say that here in simple words is good night, Mr. Drew, is a record of where all the matter was in that moment. Isn't that great? Because once you know where all the matter was in that moment, this actually gives you a way to figure out how the galaxies were formed, which is something someone was asking about. So the CMB, by the way, Mr. Drew, you should definitely you should definitely go study the cosmic microwave background radiation map, because the Big Bang did not create galaxies, but the secret, or the map to how we get galaxies, is hiding in the CMB, which we have been measuring for years and years. So there you go. Since you also asked about evidence, and there's a lot, but one that I can point to is the CMB. You should definitely look up cosmic microwave background radiation map and study it. It's been studied for 20 plus years already, but you should do it, because I think that will help incredibly to understand how the galaxies were made, okay? For the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Nearly 100 billion of them formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. Those stars, with more than about 10 times the mass of the sun, achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen, including those that compose planets and whatever life may thrive upon them. These elements would be stunningly useless were they to remain where they formed, but high-mass stars fortuitously explode, scattering their chemically enriched guts throughout the galaxy. After 9 billion years of such enrichment in an undistinguished part of the universe, the outskirts of the Virgo supercluster, in an undistinguished galaxy, the Milky Way, in an undistinguished region, the Orion Arm, an undistinguished star, the Sun, was born. I love it. So let me see. What time is it? 1:55. It's getting a little late, and we have just started the part of this chapter where we talk about the stars and galaxies. So I might just continue this tomorrow. If that's okay. And we will continue about this topic tomorrow by Neil D Tyson, Astrophysics for People in a Hurry. hopefully that was enjoyable by most. And let me know if you have any questions, concerns, any other comments before we conclude. Hello, Skeletora. Are you still here? Good night. Sorry if I was out of my lane with you. No, you were fine. Thank you for the help. Thank you so much, Skeletora. Good night. Thank you. No problem. Take care and thanks for dropping knowledge. Thank you so much. See you tomorrow. Holy crap. I just read something about my channel that... Goodness gracious me. Tell your cats. Oh, thank you. Thank you, Skeletora. All right. Thank you so much, everybody, for being here. This live felt like it was really short, but actually it's kind of late. I gotta go, and I hope to continue this topic tomorrow. We are getting into the part of the universe where we talk about stars and galaxies, which is kind of different from the very beginning of the universe. So we will continue tomorrow. There is Baji Baba sleeping on the kitty cat tree. Please do show your love, and please do rewind to see the full live. When you see this, if you're seeing this partway through, came to say bye. Hello, Abdul. How are you doing? Please do like, share, and subscribe. And please do... what was I going to say? There's Baji. Good night and sleep tight. Take care. And yes, please do like, share, and subscribe. And please do rewind if you're seeing this later, partway through. And leave us your comments if you're seeing this as a video later on. Bye. See you next time. How do I do this? Bye, bye, bye. See you next time.